Welcome to the 16th chapter on winning and proving hybrid games in the Logical Foundations of Cyber-Physical Systems textbook, where we will now begin the development of the logical characterization of the dynamics of hybrid games, with which we will be able to prove from which state which player can win a game. We'll be investigating compositional reasoning principles with dynamic axioms, but this time for adversarial dynamical systems, where each of the axioms captures the existence of a winning strategy for a more complex hybrid game, and how that relates to the existence of corresponding winning strategies for simpler game fragments. These dynamic axioms will enable rigorous reasoning for adversarial CPS models and thereby axiomatize differential game logic. Such an axiomatization turns the specification logic of differential game logic into a verification logic for CPSs, which is a cornerstone for lifting hybrid systems reasoning techniques that we've come to love and appreciate to hybrid games. We will be continuing the study of hybrid games and their logic, differential game logic. The syntax we've seen in the 14th chapter, the semantics we've seen in the 15th chapter, and now in the 16th chapter, we're looking at the third leg of the logical trinity, the axiomatics. Why is it so important to develop axiomatics? Well, because without such analysis and reasoning techniques that we get from an axiomatics, a logic that merely comes with syntax and semantics can only be used as a specification language with a very precise meaning, but that's not very helpful for actually analyzing and verifying any hybrid games. It is really the logical trinity of syntax, semantics, and axiomatics that gives logic the power to serve as a well-founded specification and verification language. We'll have a concise syntax and unambiguous semantics and actionable analytic reasoning principles. And it's all three of them that they need to be really productive. This time, we'll only look at dynamic axioms for dynamical systems for the adversarial dynamical extensions that we're looking into. And we will no longer be worrying about how to embed these in sequent calculus proof structuring principles, because after the logical sophistication that we reached right now, if only we develop the counterpart of the 5th chapter, where we worried about dynamical systems axioms for hybrid systems, if we generalize that to dynamical systems axioms for hybrid games, well, then the way we build a proof structuring mechanism with sequent calculus and so on around that is just directly unchanged. Remember, playing hybrid games is fun. Winning hybrid games, well, that's even more fun. But the most fun comes from proving that you'll win a hybrid game. There's only one thing that's kind of sort of important in it. Whenever you have a prove that you can win a hybrid game, just don't tell your opponent about the winning strategy, because otherwise he might not want to play with you anymore. What we'll learn today on the modeling and control side is how analytical and semantical reasoning techniques for discrete and continuous adversarial dynamics can be integrated and how they interact, which is important whenever you, for example, have multiple agents that interact in a cyber-physical system. We'll also see how the fixed points and semantics of repetition of hybrid games will provide one important aspect for rigorous reasoning techniques. On the computational thinking side, we'll be devoted to the study of rigorous reasoning techniques for adversarial dynamics, where we will be exploiting compositional reasoning techniques from the compositional semantics. So remember, in the previous chapter, we've captured the semantics of differential game logic and of hybrid games purely compositionally, so where the meaning of every operator is a simple function of the meaning of the pieces. And now, in this chapter, we'll exploit this compositional semantics to develop compositional reasoning techniques They also prove a property of a compound hybrid game from a bunch of properties of simpler hybrid game fragments. We'll also, again, modularly add adversarial dynamics into it by studying how each one individual operator can be reasoned rigorously in logic, where thereby we're developing an axiomatization of differential game logic. And notice a compositional semantics is, well, de facto a necessary condition for compositional reasoning principles, but it's also not a sufficient condition for the existence of compositional reasoning principles. We still will have to be clever about how we do this. On the CPS skills side, we'll develop a deeper understanding of the semantics of CPS models with adversarial behaviors by carefully relating their semantics to their reasoning principles and aligning them in perfect unison at the end of the day. That's another example how an axiomatic development shines a complementary, helpful light on semantic reasoning principles. The two of them, of course, go hand in hand. From this alignment, we'll also develop a better operational intuition for CPS effects that involve adversarial principles. In fact, before we even go ahead and do anything like this, I encourage you to go ahead to try and develop reasoning principles for hybrid games from the semantics that we saw, and then compare with what we're developing here. Let's get started. Well, first of all, we've seen the syntax of the differential game logic, where most of the operators, such as assignment and tests and differential equations, and a choice between two games, the sequential game and the game of repetition, are sort of business as usual, except right as games. But most importantly, the dual game is giving control to the opponent. So while each of the decisions of stop and go and repetition, left or right in choices, duration and differential equations, as well as responsibility of failing tests, all went to Angel, and the duality operator flipped that around to the opponent, such that all of Angel's actions become Demon's actions, and vice versa, and all of Angel's premature losing because of failing tests become Demon's premature losing because of failing the exact same tests. And the differential game logic formulas around them start like logic always does, with, for example, arithmetic comparisons and propositional connectives, quantifiers of the real still, but most importantly, for every hybrid game alpha recursively built like so, and every differential game logic formula P recursively built like so, alpha diamond P says that Angel has a winning strategy in the hybrid game alpha to reach one of the states in which the formula P is true, whereas alpha box P means that Demon has a winning strategy in the hybrid game alpha to reach one of the states in which the postcondition P is true. Remember again, Angels has this operator because, well, mnemonic Angel has wings. We've developed the semantics, which after a little bit of detour and development turned out to be surprisingly easy when done in a denotational compositional style. For example, the meaning of a game of choice is that Angel has a winning strategy to win into region X in the game where there is a choice between alpha and beta, and Angel has to make the choice. Well, whenever Angel has a winning strategy in the left subgame to make it to X, union Angel has a winning strategy in the right subgame to make it to X, and so on. And the semantics of differential game logic formulas was just a mapping that assigns every formula to the set of all states in which it is true, while the semantics of a hybrid game is a function that maps the winning conditions of the set of all states X where the game would have been won, which is determined by the postcondition, so the set of all states in which the postcondition is true, for example, to the set of all states from which there is such a winning strategy. Well, but existence of winning strategies is nice, right? But it's even better if we're also able to prove that such a winning strategy exists, not just know that in principle one of the players has a winning strategy. So let's get started. Remember one of the subtle challenges in it. The filibuster game, where it was very important in the game to make sure that while the players can stop and repeat and the opponent demon can choose left or right, it is really important for the game that while Angel can decide to repeat any number of times she wants, she can't repeat forever. She will ultimately have to stop. Because the semantics doesn't allow the players to play repetitions forever, hybrid games can be shown to be both consistent and determined. That means this by implication is true. It is not the case that Angel has a winning strategy to make it to a state where not P is true, if and only if it is the case that Demon has a winning strategy in the game Alpha to make it to a state where P holds true. In order to understand this by implication, it's useful to look at both implications. The implication goes from left to right, and the implication that goes the other way around. And it's even better to understand the intuition by first looking at the latter one. Demon has a winning strategy to make it to P in the hybrid game Alpha. Then it is not the case that Angel has a winning strategy to make it to not P. Or, rewriting this in propositional logic slightly differently, it is not the case that Demon has a winning strategy to make it to P, and simultaneously in the exact same game, Angel has a winning strategy to make it to not P. Why? Well, because that wouldn't be consistent. It cannot be that from the exact same state, these two formulas are true. The one that says Demon has a winning strategy to pull the game over into the region where P is true, no matter what his opponent Angel is doing, while also Angel supposedly has a winning strategy to pull the game over into where not P is true, no matter what the opponent is doing, because then in that case, both of the players would have a winning strategy that supposedly works no matter what their opponent is doing, but they still end up here in the state where P is true and here in the state where not P is true, and that simply isn't possible because you can't have winning strategies that pull you into two different directions, no matter what the respective opponent is doing. So consistency kind of is a given. That means at most one player has a winning strategy in every state. But what's really exciting is the converse implication that also follows from the consistency deterministic theorem, which is that implication, which I think is easier to understand if we turn it into propositional logic slightly differently, to say Angel has a winning strategy to make it into the not P state, or Demon has a winning strategy to make it into a state where P is true. That means in every state, since this disjunction is true, either does Angel have a winning strategy to reach not P, or Demon has a winning strategy to reach P. So if we give them opposing objectives, just like we did down here, then it isn't merely the case that every particular gameplay ends, because we can repeat things infinitely often, and so every particular gameplay will be won by one of the two players, but no, moreover, it's much more strategic than that. In every particular state, because this disjunction is true, does one of the two players have a winning strategy for opposing winning conditions to consistently win no matter what the opponent is trying. And that means, of course, that no matter which state you start in, it is going to be one of the players who screams victory if you give them opposing winning conditions. Now, determinacy is awesome, but of course, even if the game is consistent, so at most one player has a winning strategy, and it's determined, so at least one player has a winning strategy, that means exactly one player has a winning strategy in every state, it's still kind of useful to figure out which player that actually is, and not just know that's going to be one of them in every state who will not just win out of luck, but win consistently by a winning strategy, but also which one that is, and for what particular winning condition, and for what particular hybrid game. But we're really getting ahead of ourselves. That's where more of the axiomatic reasoning principles will come in. For the moment, let's also worry about another interesting property of hybrid games, monotonicity. So if we have two winning conditions, x and y, where y is slightly bigger, so y is, for example, this set of states where x is just that set of states, then the set of all states from which you can win into X compared to the set of all states where you can win into Y is also smaller. Or say that positively, if you have a bigger winning condition, so then you make it a bit easier to win because, well, certainly from the set of all states in which you can win into Y, these are certainly including all the set of all states from which you can win into X, because since X is contained in Y, every way of winning into X has also indirectly won into Y. It just could be easier because if you increase the winning condition, so give players a larger set of states in which you call it a victory for that player, well, then that player might have additional states in which that player has a winning strategy to win over into Y. So if this is the set of all states from which you can win angel into X, and this is the set of all states from which you can win into Y, that certainly includes all the states from which you can win into X, because every state that's in X also is in Y. And likewise also for Daemon's winning strategy. If you make it easier to win, if you give it yourself a bigger winning condition, then, well, there will also be a bigger winning region for both of the two players for that particular winning condition. So let's understand how we prove the consistency deterministic theorem and how we prove the monotonicity dilemma. Well, the consistency deterministic theorem is an induction on the structure of the hybrid game. I'll just pick on one case, the rest is in the textbook. For example, we'll need to show that this holds true no matter what the winning condition P, or respectively not P, is. So in the inductive case, we'll worry about just any arbitrary set X, which, for example, could have been the set of all states in which P is true, and so not the complement of that is the set of all states where not P is true. And then since the meaning of alpha diamond is given by the winning region for angel in the game, for in this particular case alpha choice beta, and there will be other cases to consider for that, then this is true in the set of all states that's precisely like that. This is true in the set of all states that's precisely like that, where X is the set of all states where P holds true. And then if we equate the two, we've also proved that the two formulas are equivalent. So let's do that. The winning region for the game of choice, well, that's the union of the winning regions. Okay, that makes some sense. Now, since we have the complement of the union that distributes by De Morgan's laws to be the intersection of the complements, well, but then by induction hypothesis, alpha is a smaller game than alpha choice beta. So for that one, we have already established this property, which of course in this particular formulation says the complement of the winning region where angel wins in the complement of X is the same as Daemon's winning region in the game alpha to win into X. And likewise this, the complement of the winning region for angel to win into the complement of X is the same as the winning region for Daemon in the ordinary game to win into X. Well, and now we've got the intersection of the two, but that precisely is the winning region for angel's choice of Daemon's winning strategy. So Daemon can win in angel's choice between alpha and beta to get into X whenever Daemon can win the left subgame, and he can also win the right subgame. And that's just one of the cases for the alpha choice beta subgame. The case for proving consistency and determinacy for the other operators are sort of like that. For monotonicity also, let's only look at the induction for some of the cases. I think the most subtle one is a duality case. So if we have a winning condition X that's a subset of the winning condition Y, so it's a bit easier to win into Y, well, then the complement of X is certainly a superset of the complement of Y, or equal. And because that's the case, by the inductive assumption, so the monotonicity lemma already proved for smaller sets, namely the ones for winning conditions for the hybrid game alpha, as opposed to the alpha dual case that we're currently trying to establish, well, then because X complement contains y complement, so the winning region for x complement also contains the winning region for y complement. It's a bit easier to win into x complement. Well, but that means the winning region for the dual game, and Angel does have a winning strategy for that to win into x whenever it's the complement of Angel having a winning strategy in the ordinary game alpha to win into the complement of x. Remember the pretend play, you're playing for the opponent and the opponent's goal, and whenever that doesn't have a winning strategy, you do. And that is then, because of this inclusion, everything is complemented, contained in the winning region for y, and all these complements. And the complement of the winning region for Angel in the hybrid game alpha to win into the complement of y is precisely what the winning region for the alpha duality case into y looks like. And so you've proved that the winning region into x for the alpha dual case is contained in the winning region for, again, y in the alpha dual case. And likewise, you have to worry about other operators. Here I'll do one more. For example, one other interesting operator is the repetition case, where the winning region for the hybrid repetition alpha star winning into the region x remembers this least fixed point condition. The least fixed point condition is the smallest set z such that the goal x is already contained in z, and if we ask ourselves if we were to play one more round to get into z, then we only get states that are already in z, so playing one more time doesn't make a difference. But this intersection is of course contained in that intersection where we replace to at least contain x instead to say let's at least contain the target y, because that's first of all precisely the winning region for the hybrid game repetition alpha star to win into the goal y, but also this is certainly contained in that, well, because if you bootstrap to say at least x has to be contained in this sets that you're taking the least fixed point over, then that's a bit smaller than to say that at least y has to be contained in them, because, well, again, x is contained in y anyhow. The other cases are sort of like that. Well, now we have semantical considerations with some semantical theorems for hybrid games, but wait a second, that's all nice. We were trying to develop axiomatic reasoning principles for hybrid games. How can we do that? How can we turn the consistency and deterministic principle into syntactic axiomatic reasoning principles, and how can we do that for the monotonicity principle? So adopting that this formula is valid, so the by implication between the two is true in all states as an axiom, is kind of sort of easy. All we need to do is say, well, I guess this is an axiom from now on that we can bootstrap our reasoning from. But it's not completely clear how you would adopt the monotonicity principle as an axiom. Well, why? Well, we can start with something that I guess here is rendered in logic by saying that there is a winning strategy for Angel to make it into a region about which we don't know anything at all, P, right? And if we compare that with over here there's the question, does Angel have a winning strategy to make it into another region, Q? And the fact that this is contained in that, how do we express that in logic? Well, if this is contained in that, then certainly this formula should imply that formula, because whenever this formula is true, well, since that's a state that's inside this winning region, that means the other one is true as well, because it's a state where that winning region is true. But remember, we need to do something about the assumption, right? So how do we say that this, of course, doesn't hold in general? We have no way of hoping that the existence of a winning strategy for Angel to get to P does imply the winning strategy existence for Angel to get to Q, unless P and Q are somehow related. So how do we say that X is included in Y, which of course somehow says something about P and Q? Well, the thing is, we could start to assume something like P implies Q, but it is not enough to assume this merely as an implication. because that's not strong enough. Remember, that would merely say that this implication is assumed to be true in the initial state. So in the initial state, if P is true, then Q is true as well. But what we worry about here is the several states where we're done with the hybrid game alpha already, which of course could have changed any number of variables around. So instead, the way to assume that it is really easier to win into X than it is to win into Y, because the winning region is bigger, is to instead turn this into a proof rule that says we start out assuming that P implies Q everywhere, not just in the initial state, and then we know that there is a winning strategy for Angel to get to P. It does imply that there is a winning strategy for Angel to get to Q. Let's render this in OCR character recognition text. The deterministic axiom says that Demon has a winning strategy in the hybrid game alpha to get to one of the states in which P is true, if and only if it is not the case that Angel has a winning strategy in the hybrid game alpha, same one, to get to the opposing winning condition to a state where not P is true. That's directly justified by the consistency and deterministic theorem. And the monotonicity lemma is syntactically internalized by saying, well, if P implies Q, if that's a valid formula, in other words, wherever P is true, Q is true as well, then this implication is valid as well, the one that says if there is a winning strategy for Angel in the hybrid game alpha to get to P, then there also is a winning strategy for Angel in the hybrid game alpha to get to Q, because, well, whenever she's gotten to P, she's also gotten to Q, because P implies Q is true everywhere, it's a valid formula. That internalizes this, and the demon side is internalized correspondingly. If P implies Q is a valid formula, so we've got a proof of that, well then, whenever demon has a winning strategy in the hybrid game alpha to get to a state where P holds true, then demon also has a winning strategy to get to Q in the hybrid game alpha, because all he needs to do is follow the winning strategies that he had over here to get to P, and then remember that whenever he's gotten to P, he's also in Q, and so of course he's gotten to Q. Could be true in more states, but not in less states than that. Good. We already have one axiom and two proof rules for hybrid games. All we need to do is worry about the rest. Now, of course, these are very useful axioms and proof rules, but they were not very specific to the actual hybrid game alpha that we're playing with, which is simultaneously their strength and their weakness. It's a strength because, well, that means the deterministic axiom, which means that boxes are duals of diamonds, is always useful no matter what the hybrid game is, but it isn't a good way of figuring out anything concretely for a specific hybrid game alpha. Likewise, the monotonicity principle. It's good to know that that works for every hybrid game, but at some point we need to become specific about the actual hybrid game we worry about. Which means, having adopted the deterministic axiom and the monotonicity proof rules, we'll now need to become specific about the actual operators that are in the hybrid game alpha and develop dynamic axioms for hybrid games for those cases. Let's start with the assignment case. It's perfectly possible for Angel to wonder whether she has a winning strategy in the game that's an assignment game to get to a state where P is true of X. And when is that? Well, remember the semantics of assignments. The semantics of assignments is that Angel does have a winning strategy to make it into this goal region X by the assigning the new value E to the variable X. Whenever, having done so, Angel is in the winning condition X. So if X marks the spot, if Angel wants to get to X, then she will be able to do so whenever after assigning she's in there. But how do we render this in logic now? Well, of course, it's not like she has a whole lot of choices, in fact, any at all, when following an assignment game, because it's a very deterministic game. No player gets asked anything. So there is a winning strategy for Angel, hardly any strategy at all because she doesn't get asked, to make P of X true after assigning E into X whenever, well, P is already true of the new value E that X is going to get any minute now. So if over here P of E is true, that means we're in the goal after the change. Well, then does Angel have a winning strategy after in the game where the value of E is assigned to X? That worked pretty well, but it also wasn't a whole lot of a game yet. More of an interesting game is the differential equation case. Let's characterize under what circumstance Angel has winning strategy when following a differential equation x prime equals to f of x to get to a state where p of x is true. How do we do that? Well, we've seen a whole bunch of reasoning techniques for differential equations, and of course they all still continue to be useful and valid for the hybrid games case in which you worry just about a differential equation. Remember differential invariance, differential cuts, differential weakening, differential ghost, but let's not get ahead of ourselves. Of course, these are still all legitimate, but because we've understood them so well already in the second part of the textbook, now let's make it easy again like we did in the first part of the textbook and merely worry about the case where we happen to have solvable differential equations, just because we understand the other cases so well already. In that case, if we have a solution of a differential equation, and we call that solution y, such that its time derivative at every time t is indeed the same as the value of the right-hand side, and it starts at the appropriate initial value, so actually x. Well, in that case, Angel does have a winning strategy from a state to make it into the goal x, where p of x is true. Well, whenever there is a duration that she needs to insert into the differential equation, and then follow the solution. So that's true whenever there is a time t, that's non-negative of course, that if she plugs in the particular time t into the solution y of the differential equation, then changes the value of x to assume that value from now on, then whenever p is true of x, then that of course precisely means that p of x is true after having followed the differential equation. Like that whenever we squeeze in an evolution domain constraint. Think about how you would like to do that. Compare it with the textbook after you're done with that. Now the challenge or test game. Under what circumstance does Angel have a winning strategy in the challenge game, where she's challenged to make Q true to make it into a state where P is true? Well, remember the semantics of challenges or tests. Angel does have a winning strategy in the challenge Q or test Q game to make it into X whenever she's already in X, because, well, tests don't change state, but she also needs to pass the test. That means she needs to be inside the set of all states where the test Q is true. And that, of course, means that Angel does have a winning strategy in the game where she's challenged to test whether Q is true to win into the set of all states where P is true whenever P is already true, but the test also passes, so whenever Q and P are true together. Now, what's up with the game of choice? After having taken care of all the atomic games, all the hybrid games that are not composed of smaller hybrid games, let's now worry about the case where we've got hybrid games that are composite, so they're composed of smaller hybrid games. Well, in that case, of course, we would very much like to exploit the compositional semantics of hybrid games to make sure that our reasoning also is compositional for the hybrid games. Well, when then does Angel have a winning strategy in the game of choice between alpha and the beta, where she gets to make the choice to get to a state where P holds true? Remember the semantics of the game of choice. Angel does have a winning strategy in the game of choice between alpha and beta to make it into X over here. Whenever Angel does have a winning strategy in the left subgame to make it to X. Union whenever Angel has a winning strategy in the right subgame to make it to X. Either way, she has a winning strategy of winning the game, which of course, rendered in logic, means that the formula is true whenever Angel has a winning strategy in the left subgame to make it to P, or she has a winning strategy in the right subgame to make it to P. Either way, if Angel has a winning strategy in the left subgame to make it into P, then she has a winning strategy in the game of choice, where she's asked whether she would like to play alpha or beta to make it into P, because all she needs to say, and if this formula is true, is to say, I feel like playing left today. That's all the cases up here. If instead Angel has a winning strategy in the right subgame, beta, to make it into P, well, then she had better argue for deciding to play the right-hand side subgame, beta, in the game of the choice where she's first asked. That's true in all these cases. And if both of those formulas are true, which means we're somewhere in here, well then of course it doesn't matter which choice Angel gets to make, because she could decide on alpha or beta arbitrarily. Also remember how this case, for example, directly corresponds to the semantics, right? So the semantics of alpha, choice, beta, to win into the set of all states where P is true, is precisely the set of all states where there's a winning strategy in the alpha subgame to make it into the set of all states where P is true, union the set of all states where there's a winning strategy in the beta subgame to make it into the set of all states where P is true. That's directly captured in logic up here, syntactically. Now the sequential game. Under what circumstance does Angel have a winning strategy in the game that first plays alpha and then plays beta to make it into one of the set of states where P is true? Well, if we look at the semantics again, then going to the goal X, that is possible for Angel. Angel does have a winning strategy. Whenever in the alpha, semicolon, beta game, she can make it into X, which is precisely the set of all states where she has a winning strategy in alpha to make it into the region from which she has a winning strategy in the beta subgame to make it into X. By basically just following the winning strategy, the red arrows that she had out of this region into that region, and then following the winning strategy that she had out of this region into the goal region. So first follow the red arrows, then follow the blue arrows. And that means, if we capture that in logic, we syntactically axiomatize it. It follows to say that Angel has a winning strategy in the sequential game, first playing alpha and then playing beta, to make it into one of the states where P is true, if and only if Angel has a winning strategy in the alpha subgame to make it into a more complicated goal region, the goal region that consists of all the states from which Angel has a winning strategy in the beta subgame to make it to the actual goal, P. It basically means alpha following will first be done by Angel after beta following will be done by Angel, but that goal in the beta subgame is P, whereas the goal for the alpha subgame is, well, beta diamond P, so to win to a state from which there is a winning strategy that will take her further. And the two of these formulas are for that reason precisely equivalent. The dual case, well, the previous axioms were kind of familiar. If we come to think about it, we can't possibly say that about the dual game because, well, that's new. That was never part of any hybrid system ever. So, okay. How does Angel have a winning strategy in the dual game, alpha dual, to get to a state where P holds true? Well, all right. Now we need to remember what the semantics was like for duals. Angel had a winning strategy in the dual game to win into X. Well, whenever in the complement of X, so the places where she doesn't want to be, in the ordinary game, remember pretend play, since demon in the dual game will have the choice that Angel has in the ordinary game, but she remembers that demon has the opposite objective, so he doesn't necessarily want to make X true because that's what Angel wants to make true. So if she looks at, suppose demon is trying to make the opposite happen, then in the ordinary game where Angel is playing, then whenever Angel has a way of, in the pretend play, escaping the region X that she would like to be in by making it into X complement, then these are all the sets of states where Demon would have a counter strategy, and if she then flips that region around to the complement of that, then apparently that's a set of all states where Demon doesn't have such a counter strategy, and so Angel will have a winning strategy. And that rendered in logic just precisely means that Angel has a winning strategy in the dual of alpha game to make it into one of the states in which P is true. If and only if it is not the case, then Angel has a winning strategy in the alpha subgame to make it into one of the opposite states where not P is true, which directly reflects the double complement principle in the semantics. Now, let's use these reasoning principles already for something good after we've developed them. For example, in order to understand when does Angel have a winning strategy in Demon's choice between alpha and beta. Well, what was Demon's choice? Well, remember, Demon's choice was just defined out of the double dual of Angel's choice. But let's develop it flat. When does Angel have a winning strategy in Demon's choice game? That's a derived operator, so of course we could derive a reasoning principle for it, but if we speculated directly, when would it be the case that Angel has a winning strategy in a game where Demon gets to choose? It's her winning strategy, but it's Demon's choice. Demon isn't necessarily trying to help Angel get to P. He might have different objectives in mind. So, yes, indeed. If Angel has a winning strategy in the alpha game to make it to P, that's a good thing, but that doesn't suffice because maybe Demon doesn't get to choose alpha. He might actually choose beta instead. So if you worry about the several states where Angel has a winning strategy in the beta subgame to make it into P, that's also a good indication, but not sufficient because Demon, it's his choice. He might choose the opposite. But if exactly both of those formulas are true, then Angel has a winning strategy in the alpha subgame to make it into P, and Angel has a winning strategy in the beta subgame to make it into P. So don't you worry which of the two sides Demon chooses in the end in his choice. Angel has a winning strategy regardless. That means this should be a reasoning principle, and instead of adopting it as a new reasoning principle, we will prove that it follows from the ones we already got. We will derive it as a derived axiom. Let's do so. What can we do with it? Well, we can remember what Demon's choice was like. Demon's choice is just a definition of the double dual of Angel's choice. Remember, flip the chessboard around, let Angel choose which is then Demon because of the flipping, and then flip the chessboard back in the subgames. So that means this is just, macro expansion of what Demon's choice was defined to be like. And now on the left-hand side, we have a dual, and we just learned how to handle duals in Angel's winning strategies. So that, remember, was the double knot. So that's not, but the dual goes away. Then we have, here's the axiom again. Then, never mind all the negations and things like that. Here we're asking, in this part here, whether Angel has a winning strategy in a game of choice. Never mind the sub-games, the dual here. Does Angel have a winning strategy in the game of choice? Well, of course, whenever she's got a winning strategy in the left or in the right. Here's the axiom for the job that we just developed. That means this splits into a disjunction. Of course, remember the parentheses with the negation still being in there. Then here we're asking ourselves again, when does Angel have a winning strategy in the dual subgame? All right, and so we do that over here as well, for which there was an axiom for the job. It turned it into double negation. So that means here we get a negation and another negation, but the duality goes away, and likewise here, the duality goes away by introducing a negation before and after. Right? Angel has a winning strategy in the dual subgame to make it into P. Whenever in the ordinary game, it's not the case that Angel has a winning strategy to make it into the opposite. And remember, duality flips objectives and agents around. And now what do? Well, now we don't have a whole lot of hybrid game structure left, but we've got plenty of logic propositionally here. So not of P in classical logic is of course just P, and then the not or is of course just and, just push the negation over the disjunction, which turns it into a conjunction, and you've got a double negation here, which of course goes away in classical logic, and you've got a double negation here, which just goes away. And then how we prove that? Well, that's the same formula on the left as it is on the right, so that's very easy to prove, which means from now on, of course, every time we need to worry about Demon's choice, we can do this proof again. We can also just remember the derived axiom that from now on, Angel has a winning strategy in Demon's choice to make it into P whenever Angel has a winning strategy in the left subgame to make it into P, and also she has a winning strategy in the right subgame to make it into P, and because, well, Angel never knows what Demon's going to do in his choice. Likewise, we can worry about when does Demon have a winning strategy in the game of Demon's choice between alpha and beta to make it into a region where P is true. Well, thinking about it, I guess the canonical sub-questions are, does Demon have a winning strategy in the alpha subgame to get to P? And does Demon have a winning strategy in the beta subgame to get to P? Since it's his choice between the two, whether this or that is true, he will have a winning strategy in the game of his choice between the two. In other words, the right operator, and between those two is disjunction. So this is what we should be trying to prove out of the axioms we already saw, in order to make sure that we can believe it without having to prove it from the semantics of it. So, alpha box by determinacy is the same as the double negation of the diamond modality. Demon has a winning strategy in the alpha game to make it into P, if and only if it is not the case that Angel has a winning strategy to force the opposite to make it into not P. Right? So the box turns into a diamond with double negation around it. Then we've got the question whether Angel has a winning strategy in Demon's choice. Well, we could now remember that Demon's choice was really the double dual of Angel's choice, but we just discovered a reasoning principle for the job in the previous derived axiom, so we can use that and say, when did Angel again have a winning strategy when Demon gets to choose? Well, if she's got a winning strategy in both of those outcomes, because her opponent, Demon, gets to choose. That means we need a conjunction here by the reasoning principle we just derived, and then we use a little bit of logic to distribute the not over the and by De Morgan's principle. So we've got not, Angel has a winning strategy to get to not P, or the not comes over here, and the and flips into an or. Not, Angel has a winning strategy in the beta subgame to make it into not P, and then what do we do now? Well, we use the definition by the deterministic axiom of the box modality again and say, it is not the case that Angel has a winning strategy to get to not P. Well, that's precisely equivalent to Demon having a winning strategy in the game alpha to get to P. And likewise over here, just using the axiom backwards. And now all of a sudden we've got a question that we need to prove, which is very easy to prove because, well, that's just asking whether a formula is equivalent to itself. In other words, two derived axioms that sometimes come in handy is that Demon's winning strategy for Demon's choice turns into a disjunction because it's him choosing, so it should be easier. Whereas Angel's winning strategy for Demon's choice turns into a conjunction because, well, that's harder if her opponent chooses. Note how these roles are exactly opposite to the roles were used from Angel's choice and the non-deterministic choice in hybrid systems. But that makes a ton of sense, because if it's the opponent choosing, he might just want to choose differently if he's got different objectives. Now we've developed a number of axioms for differential game logic for the box modality once and for all the cases of alpha, and it turned into a diamond modality for the assignments, for differential equations, for tests, for the game of choice, for the sequential game, and for the dual game. But we're missing the case for the repetition here. So let's worry about these. How do you prove properties of repetitions in hybrid games? So how do we prove properties of repetitions in hybrid games? Well, remember, repetitions were already slightly more subtle in hybrid systems, since hybrid games repetitions have a much more sophisticated and subtle semantics. It shouldn't be much easier, right? Okay, let's go through this. For the winning region of Angel in Angel's repetition to win into the region where X is true, remember that was the least fixed point, so the smallest set Z where X is contained in Z, and if we ask ourselves from what set of states can we win into Z by playing one more round of alpha, that's already contained in Z, but we also saw that we could have written equality here. It doesn't matter whether we ask the least equality, so the least fixed point, or the least inclusion, so the least pre-fixed point. And it basically corresponded to the principle that if we keep on asking, if we could have played one more round, how do we get into X or the region we already had? And on the one hand, we could have blown this up by an inflationary fixed point, or just indirectly characterize it as the region that doesn't change if we ask, could we get any more if we played one more round? For us, it now turns out to be easy to work from the pre-fixed point condition, where it's included in that. Well, first of all, that means since this is the least fixed point, remember that the set itself also is a fixed point, because, well, the last I checked, the least fixed point of something is still a fixed point. That means the winning region of this is equal to that. It's contained in it, but remember it didn't matter whether we'd write subset or equality here. So the winning region of repetition for Angel to make it into X by repeating alpha any number of times is equal to X itself, union the set of all states that we get to by running one round of alpha into the set we already had. So the set that is the winning region of repeating alpha any number of times to make it into X. Can we capture reasoning principles about this syntactically as axioms or proof rules instead of semantically, which doesn't help computers all that much? Well, for one thing, if we render the left-hand side in logic, then I guess what it's asking is, does Angel have a winning strategy in the game of repetition, her repetition, to make it into a state where P is true, which is like the logical counterpart of being in the region X, about which we don't know anything, because remember again, if we put in the set of all states where P is true for X, then this and that are directly in correspondence. And, well, since the two are equal, what do I know? That if they're equal, logically they correspond to the two formulas being equivalent. With the rendering of this in logic, well, I guess X, we're in the set of all states X, but which we don't know anything, but P would a logical rendering of it, because, well, the set of all states where P is true is precisely what is corresponding to X here. How do we render a union in logic? Well, I guess that's an OR. How do we render in logic the question that we can follow a winning strategy in the game alpha? Well, that was the question, does Angel have a winning strategy in the alpha hybrid game? To get into a region where something funny is true, well, what was that again? Oh, I remember, right? So the logical rendition of X, well, that's just P. And the question of this is whether in logic Angel has a winning strategy in the game of repetition of alpha to make it into that state. So I guess that would correspond to that in logic. And have we ever seen an axiom like this before? Yes, in its dual form. That's the iteration axiom. Angel has a winning strategy in the repetition of alpha to make it into a state where P holds true, if and only if, well, either she's already there or she has a winning strategy in the alpha game, so just one round, to make it into a state from which, if she were to do that again, she would have a winning strategy in the game of repetition of alpha to make it into a state where P holds true. We just looked at the core of the arguments of the soundness specification of this. Now, what is this axiom, which actually, come to think of it, is quite familiar, is internalizing about the semantics of hybrid games? Repetition. It is internalizing that, well, the one thing that the winning region of repetition is a fixed point. The alpha diamond P exactly occurs here and there. It's a fixed point of that. But it doesn't tell us yet anything about this, that it is not just a fixed point, but actually the least fixed point. So how in logic can we render the fact that the winning region of repetition isn't just a fixed point of this condition here, right, but the least of all the fixed points? Well, if it's the least of all the fixed points, then I guess one thing that we can try and do is to give ourselves another fixed point and then compare to that and say, well, but that's the least one. What does the least one mean in logic again? I guess it implies the other one. Okay, so let's develop that. That means it implies the other one. So the winning region of repetition, so where does Angel have a winning strategy to make it into P when repeating the hybrid game alpha a number of times? That's less than, so it implies Q is contained in Q. Well, but only, of course, if Q itself was actually a fixed point of this. And how do we say that Q is a fixed point of that in logic? Well, we do that in two stages. First, we say, I guess P has to imply Q, right? Because, well, X, which marks the spot, is the goal region. This is simple states where P is true. That is included in this fixed point, which means that P apparently implies Q. How do we render this in logic? Well, by asking ourselves, does Angel have a winning strategy to make it into the Q states? Because, well, Z is precisely the other fixed point we talk about. And now, how do we render the union in logic? Well, of course, by disjunction. So in other words, here we've got the least fixed point proof rule, the one that says is if Q is another fixed point of this. So it's also the case that, P, or there is a way for Angel to have a winning strategy in the hybrid game alpha to make it into a state where Q is true. If this disjunction already all implies Q, so Q is another one of those potential fixed points, then the actual winning region of repetition is the smaller one. So it is included into the full states where Q is true, which means this implication is valid. This axiom characterizes that the winning region of repetition is a fixed point, and this proof rule characterizes that among all the fixed points Q that we got, it is the least. So it implies all others. Well, the fixed point rule, you probably haven't seen ever in your life before, but it turns out from that we can derive a familiar reasoning principle for repetitions, namely for the case where we're wondering whether Demon has a winning strategy when Angel gets to call the repetitions to make it into a state where P holds true. Well, that certainly means that P had better be true right now, because if it isn't, Angel would win the game of repetition just by deciding to stop right away. What are we missing? That informs us now that P is true initially, so stopping wouldn't make Angel win, but it's still Angel's repetition, so she could do alpha again. In fact, she could do alpha a number of times again. Demon has no way of knowing how often, and every time he will have to make sure that P is true. How can you do that in a proof rule? Well, by making sure that P is true after Angel decides to play alpha one more time, provided P was still true before we even went as far as that. And that's precisely the induction principle, which of course we've seen before. The loop invariant principle for hybrid systems also is a sound reasoning principle for repetitions of hybrid games. Now, you shouldn't just take my word on that. You should ask me at this point of the latest, well, that's all nice, but can you maybe prove this? The fixed point rule followed directly from the least fixed point semantics. The iteration axiom followed directly from being a fixed point at all, but the loop invariant proof rule derives from the fixed point proof rule as follows. We start with the question that we would like to prove at the bottom and end up with the implication that it is asking is the only open subgoal, and now we have to prove it. How do we do that? Well, first, we don't actually have a whole lot of reasoning principles about boxes of repetition, so let's turn it into a diamond, for which the box axiom comes in very handy because it asks the daemon has a winning strategy of just about anything to get anywhere, if and only if it's not the case that angel does have a counter strategy to get into the counter region, so not. Well, now here we can use the converse implication formulation. P implies not that, if and only if this thing itself implies not P, which we wrote down in here. There is a winning strategy of repetition for angel to get to not P. Then, well, the opposite of that is the case, not P. Think of it this way. A implies B is equivalent to not B implying not A, shockingly, in classical logic. Now, here we can use the fixed point proof rule, right? And it tells us that we're either at the goal here is not P, and we're asking ourselves, is the other thing a fixed point? So that's this characterization, not P, or does angel have a winning strategy in one round of alpha to get to not P? Both of them already imply not P. That's directly what happens if we apply the fixed point proof rule to it. Now we say, well, but that's all nice. We're supposed to somehow turn it into the box formulation at the end. So that doesn't look very boxy to me, but we can also undo the implication flipping. So remember, A implies B, if and only if not B implies not A in classical logic. So here we can flip the negation over again. So double negation, of course, goes away in classical logic. And here we have a disjunction, which after a double negation flips into a conjunction again, and a not P on the other side, not. So in classical logic, that just goes away to P. And here we gain another negation in front of that, which is precisely what's good for us, because now we've got the question whether it's not the case that angel has a winning strategy to get to not P, which by the box axiom is precisely equivalent to the question whether the daemon, her eternal opponent, has a winning strategy in the hybrid game alpha to get to P. Well, but now we have whether P implies P and some other stuff, and P always implies P, for example, by and right. This will be proved away, and what we've got left is just the question whether P implies that a daemon has a winning strategy in one more round of alpha to still make P true. That means the loop induction principle, the proof rule, still works for hybrid games. What we've seen now is the axiomatization of differential game logic, the deterministic axiom, assignment axiom, differential equation axiom, test axiom or challenge axiom, the axiom of choice, well, of course not the axiom of choice, but the axiom of choice between two hybrid games, sequential composition game, a game of repetition, and a dual game, along with proof rules, the monotonicity proof rule I recall from a little while ago, and the more recent fixed point rule. The induction rule I don't recall from that because it merely directly derives. That's a number of very useful reasoning principles. Notice what I can also do out of these reasoning principles is to say, wait a second, alpha box P is equivalent to not alpha diamond not P, but alpha dual diamond P is also equivalent to not alpha diamond not P. So I guess from this up there and that down there, if I staple the two axioms together, I can derive that alpha box P is equivalent to alpha dual diamond P. And just concatenating the right equivalent right-hand sides, which now is a derived axiom that tells us that daemon has a winning strategy in the game alpha to make P true, if and only if angel has a winning strategy in the dual game of alpha to make P true. Well, remember, because the dual game was the one where the chessboard is flipped around, so all the actions and flip around as well. And why didn't we go for this right away? Well, because first of all, it easily derives from these two axioms, and also remember, this axiom basically followed directly from the complement formulation of the semantics of the winning region of duals, whereas that deterministic axiom up here, followed by inspecting the hybrid game alpha and doing an induction of all the shapes that alpha could have, and then worry about the winning regions of demon being a dual relationship to the winning region of angel. So that was a bit of a harder proof with this consistency and determinacy thing. And we don't want to have to do the same thing twice in order to argue that that axiom is also sound from the semantics. We merely do the simple argument of duality is double duals, and then the hard argument of determinacy, and staple the two together with a derived obvious reasoning principle to get this formulation as well. It's easier to have local responsibilities for the individual operators than to have to worry about everything at once. Having said all that, let's use the now new and improved axiomatic formulation of differential game logic for some good. For example, we can prove the dual filibuster game, that if we start at 0, angel has a winning strategy to always stay at 0, in demon's repetition when angel gets to make a choice to put 0 or 1 into the variable. Again, remember this is a filibuster situation, just dualized for the sake of illustration here. And now we remember that demon's repetition really was a dual operator. It's a double dual of angel's repetition. So that is, we can apply the duality rule, which turns it into, together with the deterministic principle, turns it into a box question of angel's repetition and the operators inside it flipped. Now we've got the induction principle that we can use, or the loop principle, to turn it into a question whether in one more round demon does have a winning strategy. Now, the box modality turns again by the box axiom into the double negated diamond modality, but it's still a dual operator. That's what this is starting with, because it's demon's choice. So if we expand out the meaning of demon's choice to be the double dual of angel's choice, then we remember that it's actually a question of having eaten up the double negation here and turning it into angel's choice. Now we have a question of angel's choice. Does angel have a winning strategy in the game where she gets to put 0 or 1 into x to make x equals 0 true? Of course, by turning this into a disjunction and then putting this assignment in and that assignment in, does the whole thing reduce the question whether if x is 0, is it the case that either 0 is 0 or 1 is 0? And yes, of course, that's provable because 0 is usually 0. So that's one example of a proof where, notice the one thing I want to call out about this proof is that in this particular style, it's a lot of flipping back and forth between boxes and diamonds and dualities and so on. So unlike in hybrid systems, where it was more or less the case that if you start proving a box property, you end up always proving a box property. And if you start proving a diamond property, for the most part, you end up always asking questions about diamond properties. Here you happily switch between the two based principle on the duality operator's occurrences. Even in hidden form, like for example, the demon's repetition really is another occurrence of two duality operators that make us flip 2 times here. Push around card is provable. Remember what that was under some assumption in the beginning. Is it true that in a game of repetition, does demon have a winning strategy even though it's angel's repetition to make sure that the position is always greater than 0? Even if he has to decide first whether he would like to push or pull on the push around card, and then his opponent angel gets to make a call whether she would like to push or pull. Well, the dynamics in the differential equation is that the position of the card changes with velocity, so the time derivative of position is velocity, while the time derivative of velocity is the sum of the two forces acting on it, is angels pushing or pulling plus demons pushing or pulling. And that we can now prove by the loop induction proof rule, to take the repetition away and ask whether the loop invariant chain implies, if we also make sure separately we're advanced enough for that that the loop invariant J does imply that x is greater or equal to 0. Let's just cover this a bit later on. Here now we have a sequential composition to worry about, which will turn it into this question. Now we've got Demon's choice of Demon's repetition. What would Demon like to do? Well, he wants to make x greater or equal to 0, well, which indirectly follows from wanting to make sure that the loop invariant is true, which of course needs to imply x greater or equal to 0. So which one is best of those two choices? D colon equals 1 is, right? So D colon equals 1, so push and then win the rest, or pull and then win the rest. The part that's going to work out is the pushing case. Fortunately, this is a disjunction, so we can weaken this away and drop it, or write and weaken. Now we've got an assignment to plug in the value of D into this. Now we've got a sequential composition, and Demon is asking himself, when does he have a winning strategy for a sequential composition? That, of course, will still split the box. Now we've got Demon has to win an Angel's choice, so he no longer gets to choose, but now he needs to win both of those cases. That will be an actual, true, honest conjunction to prove, as opposed to down there a disjunction that you can like commit to one side if you want to and then prove that. Now we basically have the value 1 drop in here and the value -1 drop in there, which requires us to prove that always when following the differential equation x prime equals v and v prime equals 2 is the invariant true, as well as x prime equals v and v prime equals 0 is the invariant true. Now, that should be very easy for a correct choice of invariant because we're speeding up and we would like to make sure that x is greater or equal to 0. But that will also be turning out to be fine at the end of the day because we're not changing velocity at all. I need to make sure that our position is greater or equal to 0. So, yes, what we read off from that is that the invariant that we're trying to have here and then use for the inductive proof needs to be that both the position and the velocity are greater or equal to 0. Because in that case, here we only keep on increasing the velocity in position, and here we never change the velocity, but the position only keeps increasing or stays stable, either of which prove that our position is greater or equal to 0. And, well, the case we skipped down here is the question whether the loop invariant does imply the postcondition. It, of course, very visibly does because it's part of it. Good. We have a proof of the push-around card. The differential equation cases, of course, are, in this case, possible merely by solving the differential equations, although we could also do differential invariants and differential cuts, differential ghost reasoning if we really wanted to. Would be straight out differential invariants in this case, essentially, with a bit of differential cut. But solving does it, just solve for all times, and we have a proof. The Wally and Eve robot dance, remember that's also provable, although I think I'll refer you to the textbook for the proof, preferably after you've done the proof yourself, because it will help you learn how to do this. The robot dance safety property, that the two of the robots always stay close enough together, because Angel does have a winning strategy to make sure that she stays close to Demon. What have we seen in our axiomatization? These fairly simple axiomatic reasoning principles for hybrid games, which, come to think of it, look quite familiar compared to the hybrid systems, but that's the good thing, where the really new case is the duality operator, and yes, all of them are compositional. Asking yourself whether you can win as Angel a game of choice is a question about the two subgames with a disjunction in between. Asking whether Angel can win a sequential composition game is decomposing into separate winning strategy existence questions. The repetition also decomposes, although as a fixed point characterization in slightly more annoying ways, because the question whether Angel has a winning strategy in the game of repetition to get to P still lurks around somewhere, but the fixed point reasoning principle actually made the loop go away. So the least fixed point and the it is a fixed point at all actually go hand in hand here rather nicely. And the duality operator also, as a new thing, is reduced into compositional ways into questions about the ordinary alpha subgame. For differential equation, well, we settled so far for simply solving it, although we could have kept differential invariants, differential cuts, and so on around. But notice, I haven't mentioned evolution domain constraints in here. Well, I could have, but it turns out there's a very elegant of just once and for all handling evolution domain constraints that really is exploiting hybrid games in a nice way. Let's look at that. How can we augment this and any other reasoning principle for differential equations in hybrid games land to capture evolution domain constraints? Well, if we're following a differential equation within an evolution domain constraint Q, then x prime equals f of x within Q, how does that compare to properties of differential equations and hybrid games that do not mention an evolution domain constraint? Well, here's a candidate. X prime equals f of x, and after that we test whether Q is true. That's all nice, but this and that game, of course, not equivalent at all, because in this one we test whether Q is true at all the times of it, and over there on that side we immediately settle for testing whether Q is true at the end of the evolution. So these two are very different. How can we reunite the two by exploiting more of the hybrid games thing? Well, we went that way, and then we can test whether Q is true at the end. How can we check whether Q has been true before? Can't stop this any earlier, then we haven't gotten very far. But what we can do to make sure that we haven't evolved here and then test whether Q is true, but we've been cheating the entire way through here because we tunneled through space that was outside the evolution domain constraint. We shouldn't have gone there ever. Basically what we can do is wherever we have gotten to at the end, invert the flow of time and check backwards. And then here, for example, we would have caught a violation of it. So what we're going to do is set up new variables, a copy of it. Z copies the value of x, and then follows the same differential equation backwards. Z prime equals minus fc, which we will march backwards now in a dual style. So under daemon's control, Angel went forward, right, but Daemon is going backwards. And then if at the end of that the test fails for the copy Z, well, then I guess Angel lost. So Angel plays forward, we revert the flow, and then Daemon checks Q backwards. That's actually not quite working out, because if not Q is true down here, then Angel would fail her test, but it wasn't really her fault, because of course in this particular case, Angel went forward and Daemon went backward, but he went too far. How can we make sure Daemon doesn't get to go back too far? Well, all we need to do is remember when we started and what time, and make sure Daemon can't go any further than that. So that means we'll remember the initial time in a state variable t0. So we look at our watch, look at what time it is. Then we follow the differential equation x prime equals f of x, which is for simplicity assumed to already contain a clock at, x naught prime equals 1. So the zeroth variable of this differential equation system without loss of generality is already tracking time. Then time will have advanced for some non-negative amount of time, and then we copy into a copy of the variable z, go backwards in time, follow z prime equals minus f of z, the opposite, the entire thing being under Daemon's control. So while Angel can evolve forward, Daemon can evolve backwards, and check. In particular, Angel will lose this test unless the evolution domain constraint is true of z. Well, but only if we're after the initial time. That means overall we're testing whether if Daemon still went to a time that is after the initial time, so in this region here, look, I made a bit of a glitch just for plotting purposes here. They should have been on the same line, but then I can't draw it anymore. Then if we're still after the initial time, then the evolution domain constraint has to be true for the copy z of the state. That means Angel plays forward, This way, we revert the flow and the time, and daemon checks whether the evolution constraint was true backwards until only the initial time, which overall is the there and back again hybrid game, which for us has the most important insight that while it's a bit longer, it is possible to define evolution domain constraints in differential equations just out of a slightly more complicated hybrid game. But notice one that nowhere, neither here nor there, involves evolution domain constraint. And that's a very good thing, because what it makes possible is for us to once and for all in hybrid games get rid of evolution domain constraint. That's one of the reasons why hybrid games are actually more fundamental than hybrid systems, because these annoying evolution domain constraints that we had to carry around with differential equations all the time, even though they're super useful in modeling purposes, they're not theoretically fundamental, at least not in hybrid games. And that's reduction is not possible like that in hybrid systems. Let's summarize what we've seen. We've seen from the compositional semantics of hybrid games, which were very easy, develop out of that axiomatic reasoning principles for differential game logic, which are just as compositional, where, for example, daemon has a winning strategy in the hybrid game alpha to get to P, if and only if it is not the case that angel has a winning strategy in the hybrid game alpha to get to the opposite, not P. Angel has a winning strategy in the assignment game to get to P of X, if and only if, well, P is already true of the new value E that X is going to get any minute now. Angel has a winning strategy when following a differential equation x prime equals f of x to get to P of X whenever there is a duration t, such that if we plug in the duration t in the solution, now we call y here, and then change the value of variable x to assume the value that the solution had at time t, and if then P is true of X for some of those times, for in particular at least one of those times, then Angel can follow this differential equation to P of X. Angel has a winning strategy in the test Q and win into P game whenever, while she's already in P, but she also succeeds with the test because otherwise she was called upon for having violated the rules of the game, which are test Q in this case. Angel has a winning strategy in the game of choice between alpha and beta to make it into P whenever Angel has a winning strategy in the left subgame alpha to make it into P, or she has a winning strategy in the right subgame beta to make it into P. In the sequential game, Angel has a winning strategy to first play alpha and then play beta to a state where P holds true, if and only if Angel has a winning strategy in the alpha subgame, such that she gets to a state from which she has a winning strategy in the beta subgame to get to P, and this is a fixed point characterization. Angel has a winning strategy in the game of repetition of alpha to get to P whenever she's already in P, or she has a winning strategy to play alpha for one round and get to a state from which she can continue further by having a winning strategy in the game of repetition of alpha to get to P. The alpha dual case, well, these were needed new justifications for soundness coming from the hybrid games. We've seen axioms like these before, but the dual case we can't possibly have seen before. Angel has a winning strategy in the dual of alpha game to get to P whenever it's not the case that Angel has a winning strategy in the hybrid game alpha to get to a state where not P is true. So remember the pretend play from the opponent's perspective with opponent's flipped objective, and then flip the entire thing around. The monotonicity principle says that if P implies Q, then having a winning strategy in the game of alpha to get to P implies the existence of a winning strategy in the same game of alpha to get to Q, because if the region that we would like to go to is a bit larger, it's implied by the old one, then the region from which we can make that happen is also a bit larger. And it is a least fixed point proof rule, the one that says if we have any other formula Q that also is a fixed point, so that P implies Q, the goal that we need to be in, having played for 0 round would make Q true, and playing one more round would already make Q true, then alpha diamond star P, so the winning region of repetition for Angel to get to P is the least of those fixed points, so it does imply Q. Overall, what we've seen is differential game logic as game logic plus hybrid games, or differential dynamical logic plus the duality operator, which we've now seen axiomatized for hybrid games and enabling us to not just know the hybrid games are consistent and determined, so from every state exactly one of the two players will have a winning strategy for opposing winning conditions, but also we have a way of finding out who that is by using the hybrid games axiom and differential game logic in order to prove the existence of winning strategies. Of course, it's the most fun you can possibly have in hybrid games because, remember, playing hybrid games, well, that's fun. Winning hybrid games is even more fun, but the most fun comes from proving that you'll win a hybrid game. Next chapter, we'll look into the soundness of the axioms that we've seen, think about how you would do that, whether it's even necessary at all. We'll look into more proofs and separation principles.